In this lesson, we will learn the change of base theorem and just make sure we know how to evaluate logarithms correctly in the calculator. So the two of the most important bases for logarithms are base 10 and base e. If the base is 10, we call it a common logarithm, and that means we don't have to show that 10 is the base. In other words, it's an understood base of 10. So if I just see log of some number, I automatically know that it means it's base 10. And that is the base that the log key, the LOG key in your calculator will use. So for example, if on your calculator you hit the LOG key and then you type in the number 10,000, if we were going to find these values and if we need to do any rounding, let's round to the nearest thousandth. We'll go 3 places to the right of the decimal. But this is basically asking 10 raised to what power gives you 10,000? The answer is 4. That one was a number that didn't need to be rounded. But if I were to put in the log of 341, 10 to what power gives me 341? That one's going to be a decimal value. And you should get 2.533. Confirm that you're putting this in your calculator correctly. Depending on the type of calculator you have, there may be a parentheses that opens after you hit the log key, and if so, you may need to close that parentheses before you hit enter or do any other operations. Some calculators may be set up to where you have to type in the number first and then hit the LOG key. So work with it to be sure you get these values correct. Notice we have a decimal number that's smaller than 1 in this last one. That should tell you my exponent has to be a negative value, and you should get negative 1.162 if you round 3 places to the right of the decimal. Notice in bold we have a little reminder here. Base A logarithms, such as this last one we looked at, when our numbers are between 0 and 1, and remember our base has to be greater than 1. In this case, we knew our base was 10. Those, when we evaluate those logarithms, we will get a negative answer back. It's got to be a negative exponent that would have given that small decimal value. Now, in many things that occur in nature, we know E, that natural number, occurs frequently, and that means finding the natural logarithm of certain things will be extremely common. We use it in economics as we look at the type of growth that can occur in nature. If you were to look at exponential decay, if you were trying to find the radioactive life of something, or if you wanted to see how quickly some bacteria is growing, you are probably going to be working with natural logarithms. And remember, that's understood to have a base of E. And that would mean we're trying to discover what would be the exponent E has to be raised to in order to give whatever that value is following the ln. So head to the next page. And what we will see is that the natural log of x could be written as log base E to the x, but that is a little less user-friendly to write it that way. So we will typically just put ln representing the natural log. So I want you to notice these will be different values because the base is different now. This is not saying 10 raised to what power gives me this number, but this is saying e to what power gives me this number. And so here's what you would see. The first one, I really wouldn't even need the calculator in order to simplify as long as I remember those properties we learned before. But if you type this into your calculator, you will see that the natural log of e to the fourth will just be 4. But look at this one. Remember a moment ago we took the LOG of 341. See what the ln, the natural log of 341 is. It's a larger number. It's 5.832. And the natural log of this decimal value, again, because it's a decimal number between 0 and 1, we should expect a negative answer back. It would take a negative exponent to give that to us. And indeed, we get negative 2.675. So please be sure that you're entering these things into your calculator correctly. Now, this is the part that you want to be sure you understand how to use correctly. We have something called the change of base theorem. If you remember, I told you your calculator only has the LOG key, which uses base 10, and the LN key, which uses base E. So if you look at this example on A, and you're supposed to evaluate log base 4 of 20, we wouldn't have a way to do that in the calculator unless we know what the change of base theorem says. And if you'll look in this box, it gives us a tool to turn it into something that the calculator can then evaluate. So if we have the log of some base other than 10 of a number, then that would mean we can change it into a base 10 to put into the calculator, and we would get the correct answer if we do it in this way. You would always put log base 10 of whatever the value is after the base when it's in exponent form. So it would be log base 10 of x divided by log base b of a, whatever the original base is. So remember, you're going to be dividing by the log of the original base in the denominator. And that would tell us that for log base 4 of 20, if we were to type log 20, now remember in your calculator you'll want to put that in a parentheses, then divide it by, in another parentheses, the log of 4, we will be able to get the correct answer. Because I know if I tried to put that into exponent form, 4 to the x power equals 20, I wouldn't know what that is. But if I simplify this, my calculator will tell me 2.1610. If I went ahead and went 4 places to the right, if I just go 3 places, it's 2.161. Now, remember we said this means 4 raised to what power gives us 20? See if this answer is logical. I know 4 to the second power is 16. 4 times 4 is 16. But 4 to the third power is 64. Doesn't it seem logical? It would have to be just a little bit more than 2, but not very much more than 2. That's the power of the change of base theorem. It gives us the ability to put it into a base that our calculator understands. So if you look at the second example, all you would have to put into your calculator would be the log of 0.7, put those in parentheses, divided by, my denominator would be the log of 2. And if I were to do that, I will end up with a negative value, and I know that because that log of 0.7 has to be a negative number. That was something that was between 0 and 1, and I actually get a negative 0.5146 if I went 4 places to the right of the decimal. Again, if this were back in exponent form, it would mean 2 raised to what power would equal 0.7. Well, the only way I can put an exponent on that and get something that's smaller than 2 is if that happens to be a negative exponent. So that answer is logical. And that's all there is to the change of base theorem.